We looked at the one-to-one property earlier, but let's review it. So the one-to-one property says that if b to a power equals b to a power, then those powers have to be equal in order for the same base with an exponent to be equal. So, I don't know if this makes sense, because I'm trying to think, what if we had like 3 squared? Sometimes it just helps if you put numbers to it. So if we had 3 to the second power equals 3 to the second power, then obviously 2 equals 2, right? So technically the first statement means that 9 equals 9, which is true, but it's also true that 2 equals 2. So if the bases are the same and the exponentials are equal to each other, then the exponents have to be the same. And based on that, we can use that to solve where we don't know an exponent, like there's a variable. Okay. So let's look at example 3, part 1 here. We've got 9 to an x power equals 1 over 27. Well, both the numbers 9 and 27 can be rewritten with a common base of 3. So I'm going to use common bases to rewrite what I can. So I'm going to take my 9 and rewrite it as 3 to the 2x, because 9 to the second power, 3 to the second power is the same as 9. So 3 to the 2x means the same thing as 9 to the x. And then the other side of my equation can be rewritten as 3 to the negative 3. See if you guys can understand why that would be true. Because 3 to the third power is 27. So if it's 1 over 27, then we need that negative exponent to turn into the reciprocal. So 1 over 27 is the same thing as 3 to the negative third. So just a little side note, 3 to the third is 27. So 3 to the negative third is 1 over 27. Hopefully that makes sense. Just a little, side thought process here. Okay, so look, we've got our one-to-one property right here in front of us at this point. We've got 3 to the 2x equals 3 to the negative 3. We have the same base of 3 on each side. We have the two expressions are equal to each other. So based on this property, that means the exponents have to be equal to each other. So we can say that 2x equals negative 3, and therefore x equals negative 3 halves. And we just solved that exponential equation by using common bases, or using our one-to-one property of exponentials. I don't know if you want to try problem 2 on your own. Like, just look at it for a second, see if you could figure out what a common base would be that you could use to solve it. Let's go ahead and do part 2 together. So we have 2 to the 3x power equals 16 to the 1 minus x power. 2 and 16 can both be written as a base of 2. So 2 to the 4th power, I think it is. 2 to the 4th power equals 16. 2 times 2 is 4 times 2 is 8 times 2 is 16, correct? So we can rewrite this as 2 to the 3x equals 2 to the 4th. But then the weird part is it still has this 1 minus x exponent thing that has to stay the same, because all we did at this point was change our 16 to a 2 to the 4th power. So now we can't forget just little algebraic rules like distributive property here. Okay, so that's going to take our 2 to the 3x stays the same on the left, but on the right we'll have 2 to the 4 minus 4x, because we had to change our 16 as 2 to the 4, and we had to leave our exponent of 1 minus x, so that meant we needed to distribute that 4th root for that to be accurate. Now we have our one-to-one property, where each side has the same base of 2, which indicates that our exponents will be equal to each other. So we should just be able to take our exponent 3x equals 4 minus 4x and solve for x. So I'm going to add 4x over here, so it gives me 7x, and I'm going to divide both sides by 7, so x equals 4/7. Yeah, we can get some pretty weird answers, but there's another exponential equation solved by using the one-to-one property.